Swayam Prabha. Digital India. Educated India.
So, now in the earlier class you have seen that if I know the Laplace transform of a function, then what will be the Laplace transform of derivative of the function, that we have done, and what will be the integral Laplace transform of the integral of the function, that also we can find out. Now, let us see the next one, that is multiplication of power of t. If Laplace transform of f t is f s, then Laplace transform of t into f t equals minus f dash s. Means, if I know the Laplace transform of f t, then if I multiply the function by t, then Laplace transform of that function t into f t will be nothing but minus f dash s, that is minus derivative of the function. Let us see the proof. So, your f s is nothing but Laplace transform of f t, and this is equals 0 to infinity e power minus s t into f t dt. So, what is your ddS of f s? Your ddS of f s is nothing but your ddS of this integral, that is 0 to infinity e power minus s t into f t dt. This is the derivative of this, and using the differentiation under the integration, this we can write down 0 to infinity your del s of e power minus s t, sorry, this will be e power minus s t into f t dt. So, that you can evaluate this one, and this whenever I will integrate 0 to infinity, this becomes, if I use the differentiation under the sign of integration, minus t will come here e power minus s t into f t dt. So, this equals, again I can write down nothing but minus will come outside 0 to infinity e power minus s t into, it becomes t into f t dt. So, this is 0 to infinity e power minus s t into t into, this is nothing but t into f t dt. So, that your function becomes, this is nothing but what, Laplace transform of t f t. So, that this equals Laplace transform of t into f of t. So, this completes the proof that if I know that the Laplace transform of f t is f s, then Laplace transform of t of f t, this is nothing but ddS of f s or minus f dash s, sorry, one minus sign will come over here. One, this is equals to, I can write it simply, minus of, this minus sign is there, Laplace transform of t f t. So, that I can write down Laplace transform of t f t, this is equals to minus ddS of f s, which is nothing but f dash s. So, let us just see this one, as what we have told, your f s is this. So, from here ddS of f s is ddS of 0 to infinity this thing using differentiation of under the sign of integration, we are writing 0 to infinity del s of e power minus s t f t dt. This is equals 0 to infinity minus t into e power minus s t f t dt, and minus can come downwards. So, e power minus s t t f t over the integral from 0 to infinity, and this is nothing but minus Laplace transform of t into f t, and therefore, the Laplace transform of t into f t, this is equals minus f dash s. Let us see the next theorem. If Laplace transform of f t equals f s, then Laplace transform of t power n, earlier was t f t equals f s. This we are saying that Laplace transform of t power n into f t, this is equals minus 1 to the power n dn dsn of f s, where n can take values 1, 2, 3 like this. So, Laplace transform of t to the power n into f t equals minus 1 to the power n ddn of ddn dsn of f s. Let us see how we can complete the proof. We are assuming, of course, by induction we will show it. We are showing that the theorem is true for n equals some value of n, that is equals r. So, that you can write down minus 1 to the power r f r s, this is equals to 0 to infinity e power minus s t into t to the power r into f t dt. We are coming from here. You know this thing, minus 1 to the power r f r s, it is true. So, that you can write down this thing. So, minus 1 to the power r into f r plus 1 s, what will be this value? This value is nothing but minus 1 to the power r plus 1 will come over here into dr, this is equals to dr plus 1 ds plus ds to the power r plus 1 of your f s, that is your f s is this thing. So, this is equals, again you can write down minus 0 to infinity del del s of e power minus s t, del del s of e power minus s t into t to the power r into f t dt. So, this is you are getting from this integral earlier theorem dr plus 1 drs plus 1 f dash s. If you remember, if I know the value of the integral, then Laplace transform of dr dr plus 1 also we will get from here. So, this is equals minus 0 to infinity minus t into e power minus s t into t to the power r you will get, and into f t dt you can write down by using this. After this differentiation you will obtain this, and this equals you can write down 0 to infinity e power minus s t into, this is nothing but t to the power r plus 1 into f t dt. So, you are getting this thing, that this equals this minus will be cancelled, e power minus s t into t to the power r plus 1 f t dt. And so, this is basically e power minus s t into g t dt, where g t is t to the power r plus 1 f t into dt. So, you can write down this as Laplace transform of t power r plus 1 into f t dt, sorry, into Laplace transform of this. So, we are showing that Laplace transform for Laplace transform of f to the power r f t to the power r f r is true. Then for Laplace transform of t to the power r plus 1 f t also it is becoming true. So, from here actually I made a mistake. I think this should be, this one should be minus 1 to the power r plus 1, because this was minus 1 to the power r and we replaced r by r plus 1. So, this quantity is wrong, and this will be replaced by minus 1 to the power r plus 1 f of r plus 1 s. So, we are showing that this is true by mathematical induction. It is true if it is true for, we assumed it is true for n equals r. We are proving that it is true for n plus n equals r plus 1. So, that if n equals 1 it is true, it will be true for n equals 2, subsequently for n equals 3, and like that way, and this completes the proof of the theorem. Quickly let us go through the next parts of this. We are assuming first it is true for n equals r. So, that minus 1 to the power r dr dsr f s, that is f to the power r ds equals Laplace transform of t to the power f t, and from definition this is nothing but 0 to infinity e power minus s t t to the power r f t dt. So that minus 1 we are assuming starting from minus 1 to the power r plus 1 f of r plus 1 s. This is equals, we are writing this, which is nothing but minus del s of e power minus s t into t to the power r f t dt. From earlier theorem we got this thing. From here we are getting minus 0 to infinity minus t into this quantity, and which is nothing but e power minus s t into t to the power r plus 1 f t dt. So, this is again nothing but Laplace transform of t to the power r plus 1 f t. So, that we are showing that if it is true for t equals r, it is true for t equals r, if it is true for n equals r, it is true for n equals r plus 1 also. So, if it is true for n equals 1, it will be true for n equals 2, n equals 3 and subsequently like that. It is true for any positive integer n. Now, let us come to the division by t. If Laplace transform of f t equals f s, then Laplace transform of 1 by t f t. Earlier one, if you see that we are multiplying t by f t and we are getting that. Now, if you divide f t by t, then Laplace transform of that function f t by t is equals to 0 to infinity, s to infinity f x dx, provided we are assuming, one assumption is there, that Laplace transform of t approaches 0, 1 by t f t exists. So, let us see this one, provided this thing, we are assuming g t equals 1 by t f t. Means I know the Laplace transform of f t is f s. I am assuming the function g t as 1 by t into f t. So, that from here simply I can tell that f t is nothing but t into g t. From here I can tell that. So, Laplace transform of f t, if I write down, then Laplace transform of f t, this is equals f t is t g t. So, I can write down Laplace transform of t g t, and this is nothing but, again we have done the property, Laplace transform of t into this is equals minus d d s of Laplace transform of g t, using the earlier theorem whatever we have done now. So, that Laplace transform of f t, that is f s, equals minus d d s of Laplace transform of g t. So, we are getting now your this thing f s is minus d d s of Laplace transform of g t. If we integrate from s to infinity f s d s now, on both sides we are integrating this. So, that we will obtain minus Laplace transform of g t, and the integral will come from s to t, will be from s to infinity. So, that this equals, you can write down limit s approaches infinity Laplace transform of g t plus Laplace transform of g t, because this is t is independent of s. This value as s approaches 0, Laplace transform of any function approaches 0. This we can always prove it, Laplace transform of g t, this equals as s approaches infinity. You can tell that this you can write over here that Laplace transform of g Laplace, sorry, not Laplace upon, limit s approaches infinity Laplace transform of g t, this is equals limit s approaches infinity 0 to infinity e power minus s t into g t into d t, and this value e power as s approaches infinity, this term vanishes. So, that it is equals to 0. Therefore, limit s approaches infinity Laplace transform of g t, this term vanishes. So, you are having only equals to Laplace transform of g t, that is 0 plus Laplace transform of g t. And what is g t? G t is nothing but f t by t, Laplace transform of f t by t. So, that Laplace transform of f t by t, this vanishes. Laplace transform of f t by t is equals to this s to infinity f s ds, which completes the proof. Let us quickly see it on the screen itself, so that you can view it properly. Laplace transform of g t is 1 by t into f t. So, your f t is t into g t, and Laplace transform of f t is Laplace transform of t g t. Using the theorem, you are writing minus d d s of Laplace transform of g t, or f s you are writing this. Now, f s s to infinity is there. So, you are integrating on both sides of the last equation from s to infinity. So, s to infinity this is equals minus, because it was d d s of this Laplace transform of g t. If I integrate, I will obtain only this function Laplace transform of g t. S varies from t varies from s to infinity. So, that it is limit s tends to infinity Laplace transform of g t plus Laplace transform of g t. This Laplace transform of g t vanishes, because s approaches infinity, Laplace transform of g t is this, and this function is 0 as becomes 0 as s approaches infinity. So, that you are obtaining 0 plus Laplace transform of g, which is g t is Laplace transform of f t by t. So, please note this one, that the Laplace transform of, if Laplace transform of f t is f s, Laplace transform of f t by t, that is if you divide the function by t, is equals to s to infinity f x dx, where f x is basically Laplace transform of f x. Now, let us do certain examples on these properties and theorems, whatever we have done just now. The first one is, say, Laplace transform of t into cos a t. Here we have to find out Laplace transform of t into cos a t. So, if I use this theorem, this is equals to minus d d s of Laplace transform of this cos a t, Laplace transform of cos a t using the theorem. And you know already the if Laplace transform of cos a t, we know it, this is minus d d s of Laplace transform of s by s square plus s square. Sorry, minus d d s of Laplace transform will not come, simply minus d d s of s by s square plus s square, because this is the Laplace transform of cos a t. And this is equals, if you evaluate the differentiation, you will obtain the result as s square minus s square by s square plus s square whole square, where your s is greater than 0. So, you see the usefulness of the theorems and properties. If I have to do it directly, then I have to evaluate the integral t cos a t from 0 to infinity into e power s t. Whereas, using this property directly, I am writing minus d d s of this, and only one differentiation I have to do, and I am getting the required result. And so, you are getting this minus d d s of this, and you will obtain the result as this one. Now, find the Laplace transform of t square sin a t. If you see here, Laplace transform of t square sin a t, whenever you are writing, this equals, you can use the derivative of t to the power n f n. We know, if I know the Laplace transform of f t, then I can find out the Laplace transform of t power n f t also. So, using this formula, this will be minus 1 to the power n, here n is 2. So, minus 1 whole square into d square d s square of Laplace transform of sin a t. And already we know what is the Laplace transform of sin a t. So, that this you will obtain d square by d s square of a by s square plus s square. And if I evaluate the result, here I am directly writing, because only thing you have to do, derivative this function a by this thing twice. So, 2a into 3a square minus a square divided by a square plus a square to the power whole 3, where a is greater than 0. Again you see the function is complicated, but I am getting this thing using the formula theorem. I am writing it as in terms of formula and twice derivative, making derivative I am getting the result of the Laplace transform, because always we know that differentiation is little easier compared to the integration. Let us again see it, this one Laplace transform of sin a t is this. So, that you are getting dds of this, and from here you can obtain this result dds 2 power 2 by 2a into 3a square minus a square by a square plus a square to the power whole cube. You see this complicated function, find Laplace transform of cos of root t by root t. For this one, we are assuming, say, your f t is equals to sin of root t. I will tell you why I am doing it. So, that your f dash t, I have to find out the Laplace transform of cos of root t by root t. I am starting with a function sin of root t, which is I am assuming as f dash t, f t. Now, whenever I will make f dash t will be cos of root t by 2 root t. I think now you can understand why I started with sin root t, because once I am making the derivative, then I am getting the cos root t by root t form, and also here your f 0 is equals to 0, we know it. And also I know this thing, Laplace transform of f dash t equals s into Laplace transform of f t minus f 0. So, once I am writing this, therefore, what is your f dash t? F dash t is cos of root 3 root t by 2 into root t. This is equals s into Laplace transform of f t, that means s into Laplace transform of sin root t. This already sin into root t. This f 0 is 0 from here. So, this term will not be there. So, this is s into Laplace transform of sin of root t, and once I am writing this, therefore, I know what is the value of Laplace transform of sin root t, already we did it earlier. So, that Laplace transform of cos of root t by root t, this is equals root over, I am again writing it in one go, e power minus 1 by 4 s. This will be the result. So, although the function was complicated, but we just took here f t equals sin root t, from there f dash we are finding out, and Laplace transform of f t I know s into this. So, although I have to find out the Laplace transform of cos root t by root t, I am actually finding out the Laplace transform of sin root t, which already we have done earlier, and we are getting this result. Again, let us come back to this. I am just quickly going through this f dash t, already I have discussed this one, and you will obtain the required result. Next is this thing we are writing like this. Next example, we are saying that first you prove that Laplace transform of sin t by t equals tan inverse 1 by s. Then once you have find it, then find out the Laplace transform of sin a t by t, and also check whether the Laplace transform of cos a t by t exists or not. From this proof, we are saying that the Laplace transform of sin a t by t will exist, but Laplace transform of cos a t by t may not exist. So, to prove this one, again we are starting with, say, f t equals sin t. We are starting from this one. You know that limit t approaches 0 f t by t, this is equals, then limit t approaches 0 sin t by t, which is equals 1, and also your f0 is 0. This is required for the theorem. And we know this thing, Laplace transform of sin t is equals to 1 by s square plus 1, which is equals to say f s, what we are assuming. Now, using the integral Laplace transform of sin t by t, this equals, you can write down s to infinity f x dx, and this is equals to s to infinity your f x is f s is 1 by s square plus 1. So, that it will be dx by x square plus 1, and I know the standard integration, this is tan inverse x. So, that this will be equals to tan inverse x from s to infinity, and this will be pi by 2 minus tan inverse s, which again you can write down nothing but cot inverse s. This equals cot inverse s is again nothing but tan inverse 1 by s. So, this completes the first part, that the proof that Laplace transform of sin t by t is equals to tan inverse 1 by s, and therefore, this is true. Next, the Laplace transform of sin t by t, since it is tan inverse x, so it exists. Now, come to the second part of the problem, that is Laplace transform of sin a t by t. This equals, I can write down a into Laplace transform of sin a t by a t. So, that it will come in the form of Laplace transform of sin t by t format, which already we have done it. This is equals 1 by a tan inverse 1 by s will be replaced by only s by a. Here t was there, it was s. For a t equals, when t is there, here it comes s, when a t will be there, it will be then s by a. So, that this is equals tan inverse a by s, we can write down. And the last part of this problem, this is the second part, that so that Laplace transform of sin a t by t is tan inverse a by s. The second part was the cos a t by t. We know that the Laplace transform of cos a t is equals to s by s square plus s square, which is equals to say f s. So, that Laplace transform of cos a t by t, this will be equals to s to infinity, again from here x by x square plus s square into dx. Again this is the standard form, that is it will come in the form of log. So, that half into log of x square plus s square s to infinity, and this is equals to half into limit x approaches infinity log of x square plus s square minus half into log of, if I put the lower limit, it will be s square plus s square. Now, you see this particular limiting value, limit s approaches infinity, x approaches infinity log of x square plus x square, which goes to infinity, that means does not exist, which does not exist this limiting value. Since the limiting value does not exist, therefore, Laplace transform of cos a t by t also does not exist. So, I hope it is clear, although Laplace transform of sin a t by t exists and it has a finite value, Laplace transform of cos a t by t does not exist. Just quickly let us see this one. This was the problem. So, at first we are showing Laplace transform of sin t is 1 by s square plus 1. From there you are telling Laplace transform of sin t by t s to infinity. You are evaluating the integral, you are obtaining the result as Laplace transform of sin t by t as tan inverse 1 by s. The next part was Laplace transform of sin a t by t, which you are writing a into Laplace transform of sin a t by a t. So, that the in this form you can directly write down a into 1 by a tan inverse 1 by s by a, which is nothing but tan inverse a by s. So, Laplace transform of sin a t by t is tan inverse a by s. Now, for Laplace transform of cos a t by t, you are assuming first Laplace transform of cos a t is this s by s square plus 1. So, that Laplace transform of cos a t by t you can write down s to infinity this integral, and this is equals to, if I evaluate the integral, it will come in terms of log, and once I am getting it in terms of log, then it will be half into limiting value of this. This limit extends to infinity, log of x square plus a square does not exist. Therefore, the Laplace transform of cos a t by t does not exist. So, thank you. In the next class, we will go for some more examples.